In the previous graph we showed how corner solutions can emerge when indifference curves cross one or both of the axes. In this graph we'll show how we can simply assume away corner solutions if we're willing to assume that indifference curves don't cross the axes. To do this, we turn to the example of my wife choosing between sugar packets and iced tea glasses. We assume that she has $15 to spend, that sugar costs 25 cents a packet, and that iced tea costs 50 cents a glass. If she were to spend all her money on sugar, she could buy 60 packets of sugar with her $15 at 25 cents a packet. Or she could spend all her money on iced tea, in which case she could buy 30 glasses of iced tea with her $15 at 50 cents a glass. Or she could do anything in between, giving us this budget constraint. When we first introduced my wife's tastes over sugar packets and iced tea, we treated my wife as being rather obsessive-compulsive, needing exactly 1 pack of sugar for every glass of iced tea and being able to gain no additional enjoyment from any additional sugar or any additional iced tea unless they came in pairs. In other words, we treated my wife's tastes over iced tea and sugar packets as tastes over perfect complements, as depicted by the 3 indifference curves graphed here. To see where my wife optimizes, we again have to combine the information we have about her tastes with the information we have about her budget constraint. We begin by transferring her budget constraint onto a separate graph in panel C. We then similarly move my wife's indifference curves onto panel C, and we notice that the highest possible indifference curve my wife can reach is the blue indifference curve. It contains a point that lies in her budget constraint, point A, and any higher indifference curve contains no points in the budget constraint. So A is the best that she can do given her circumstances. Point A in panel C is clearly an interior solution. It doesn't lie on any corner of a budget constraint. But we don't have to go to the extremes of perfect complements to guarantee that our solution will be an interior solution. In panel D, we start with the same budget constraint again, but now we'll switch to tastes that are less extreme than perfect complements. We do this by taking away the corner that the previous indifference curves exhibited and adding some curvature everywhere. By doing so, we're allowing iced tea and sugar packets to be somewhat substitutable, but not perfectly substitutable. Finding the optimal bundle for this consumer again involves combining the budget constraint and the tastes as represented by these indifference curves, so that we can identify the highest possible indifference curve the individual can reach, while still remaining within the budget. We can then easily see that the highest possible indifference curve that this consumer can reach is the blue indifference curve, which contains 1 bundle that lies within the budget constraint, with all bundles above it, all bundles that are preferred, lying outside the budget constraint. The optimal bundle then is bundle A, which contains 30 sugar packets and 15 glasses of iced tea. This bundle A is every bit as much an interior solution as the bundle A that we got in panel C, where we had assumed the tastes were those for perfect complements. We therefore don't have to resort to the extreme assumption of perfect complementarity to guarantee that the solution for the consumer is in fact an interior solution. Rather, all we really need is to assume that the indifference map is such that none of the indifference curves cross any of the axes. If that's the case, no corner solution can emerge, and any optimum will therefore be an interior solution. We concluded our discussion of graph 6.3 with the observation that just because indifference curves do cross an axis does not necessarily mean that the solution will be a corner solution. But assuming that none of the indifference curves cross an axis allows us to say definitively that there will not be a corner solution.